Okay, let's have a very quick look at a few trends of the periodic table. We're going to very briefly check out the atomic radius, the ionization energy, the electronegativity, and the melting and boiling points, just the trends of these four areas. So we'll start with atomic radius. Now, what is the smallest atom? Hydrogen, right? Well, actually, no, that's not the smallest atom. The smallest is actually helium. Hydrogen is the lightest. Check out its atomic mass, 1.008. Helium's is essentially 4 times that. So sure, hydrogen is the lightest, the least massive of all the elements, but it is not the smallest. We have a trend that as we go across the periodic table, the atoms get smaller. They decrease in size. And as we go down a periodic table, the atoms increase in size. Okay? Here's a chart that shows this trend. So hydrogen to helium, it doesn't look like there's much difference in size, but helium is smaller. Okay, we can see coming from the group 1 and 2, the S block elements, into the P block elements, there's quite a marked difference there. And then once we're in the P block, then the difference becomes less pronounced. Okay, but the trend is there. As you go across the periodic table, the atoms get smaller. Let's take a quick look at what's actually going on. So here's a nucleus positively charged, and here is an electron booging around that nucleus, right? So the electron's going round and round, yep. What that electron is actually trying to do is go in a straight line, okay? At any given moment, that electron is going straight line, according to Newton's first law of motion, that an object will remain in constant motion unless acted on by an outside resultant force. Right, well, constant motion, that is a straight line, because if it was turning, that's not constant, that's acceleration when you turn. So that electron is trying to go off in a straight line, but it's not, it's going around and around the nucleus. Well, why is it not going in a straight line? Because there is an outside force acting on that electron. Now, that outside force is the attraction that the negatively charged electron has towards the positively charged nucleus. Okay, so we have nuclear attraction there. And that's a force that is applied to the electron, and that changes its motion. In this sense, we're talking a change of direction, right? That electron is constantly accelerating towards the nucleus, just never quite hitting it. So there we go. We have attraction between the negatively charged electron and the positively charged nucleus. That's what's essentially holding the electron in its shell and orbit, going around and around the nucleus. Okay, so that's hydrogen, right? 1 proton, 1 electron. Let's draw the nucleus of helium. 2 protons in there. Helium has 2 electrons. However, we have more nuclear charge now, right? More positive charges. There are 2. Now that extra charge, those 2 positive charges, are going to be attracting the electrons more strongly. So instead of out there, sort of, same distance as the electron for hydrogen, these electrons are actually going to be found closer in. Okay, so they're closer to the nucleus. So that electron shell is essentially smaller. Wow, bad circle, but you get the idea. There we go, a little bit better. You get the idea. That electron shell is smaller than the electron shell for hydrogen. So the atom just got smaller. Okay, so this is why atoms get smaller as you go across the periodic table, as you go across one row or across one period, because every step you take, you are successively adding more and more protons into the nucleus. All right, remember, the periodic table is sorted by atomic number. That's the number of protons. Let's look at the second period now. We have 3 protons, 4 protons, 5, 6, 7, 8, 9, 10. So we get more and more protons as we go across the periodic table. Well, more protons means that the electron shells are drawn closer to the nucleus. Okay, there's a stronger nuclear attraction from those extra protons. That's why the atoms get smaller as you go across a period. Okay, now let's look at why they get larger as you go down. Let's just get rid of this. Another diagram required. Okay, so let's have a nucleus. All right, we'll start with, I guess we'll start with hydrogen. It just has a proton. In fact, I'm not going to draw the pluses anymore. I'm just going to write a P plus for proton. And the electron shell, let's say it's here. Okay, there we go. There's hydrogen. Now, we drop down, we go to lithium. Lithium actually has 3 protons. Now, the first thought you might have is, well, okay, that electron shell is going to be drawn closer in now because we have extra nuclear charge. That's what we were just saying. When we have more protons, the electrons are closer. Well, yes. Okay, let's draw it in closer because we do have extra protons, so that electron shell is closer. Now, it's smaller, yeah, but we have another shell, don't we? Okay, the first shell can only take 2 electrons. Now we have to add another shell. And you'll notice that when we add that next shell, it's further out. Okay, so we actually only have 2 electrons in the first shell. We've got another electron in this next shell. And then as we go down, sure, we are adding more protons as we go down a group, but we're adding another entire shell as well. And that next shell lies further out. Okay, so hopefully that makes sense to you. So as you go across a period of the periodic table, remember a period is a row, a vertical column is a group. As we go across a row, we have more protons, but the same number of electron shells. Okay, the number of shells is not changing, so those shells that we already had are just getting pulled closer and closer to the nucleus. As we go down a group, we have more protons, but we have another shell as well, and that shell is further out. So that's atomic radius, and hopefully that makes sense. Next one we're going to look at is ionization energy. Ionization, what could that be about? Well, ion, yeah, we're making an ion. Okay, so the ionization energy is actually the energy required to move an electron from an atom or an ion. It could already be an ion, but you're trying to remove another electron. But this is in the gaseous state, right? So essentially, it's how hard is it to remove an electron. Now, the trend for this one is that as you go across the periodic table, the ionization energy increases. As you go down the periodic table, the ionization energy decreases. Okay, so essentially it's the opposite to the atomic radius. Now, how are we going to explain this? Oh, wait, let's look at a quick chart first. Here we go. Here is the ionization energy of the main block elements. By main block, we're talking the S and P elements. And you can see it definitely goes up, right? The trend that we see in front of us is as we go across the table, the ionization energy increases. Right? Now, what's going on? Well, remember we just talked about there being more and more protons as we go across the periodic table, and more protons gives us more and more plus charges. So, firstly, yeah, sure, okay, the shells are drawn closer to the nucleus. That makes the atom smaller. Great. But also those extra pluses, like in boron, we've got 5 protons, and then we have 6 protons, and then we have 7 protons, and we have 8 protons, right? These elements are listed according to the atomic number, the number of protons. Well, we have more and more nuclear charge, so more and more attraction to those electrons, which is what we mentioned just before, but that means it's harder to pull an electron off. Remember, ionization energy is the energy required to remove an electron. Okay, but if those electrons are being held more strongly because they're more strongly attracted to the extra protons, it's going to be harder to remove one. Right? So it takes more energy to do that. So the ionization energy increases. Now, going down the periodic table, down through the rows, remember we have extra electron shells which are further out from the nucleus, which means the attraction that those valence electrons have for the nucleus is going to be less and less and less because the electrons are further and further away. Okay, so the ionization energy decreases as we move down a group because the valence electrons, I should say, are further from the nucleus, okay, because they're in a new shell, it's further out. It's also due to this thing called electron shielding. Let's just scroll that here. We have electron shielding. Now, electron shielding is essentially those outer electrons don't get the full attractive force to the nucleus. They don't get that full impact because they're sort of blocked from the electrons of the shells within them, like closer into the nucleus. So we refer to that as electron shielding, right? So firstly, the electrons are just further and further out because we're adding another shell. So the ionization energy is decreasing because they don't have that same attraction to the nucleus. But another reason they don't have that same attraction is it's sort of blocked from it from the electrons that are, essentially underneath them, right, in shells closer to the nucleus. Okay, next one up is electronegativity. Now, the thing about electronegativity is that it tends to follow the ionization energy. Right? So electronegativity, actually we should say what that is. Well, this is the attraction that an atom has for a bonding pair of electrons. Okay, so when you get into bonding, you'll realize that a bond is 2 electrons. Okay, a chemical bond is 2 electrons. So the attraction that an atom has for those electrons is referred to as the electronegativity. Now, firstly, let's just state that the trend is the same as the ionization energy. As you go across the table, the electronegativity increases. As you come down the table, it decreases in much the same way as it did for the ionization energy. Now, here's the thing. The reason is pretty much the same as well. Okay, so it's the attraction that you have for the bonding electrons, which is basically the same as saying the attraction you have for the valence electrons. Well, as we go across the table, we have more and more protons attracting those valence electrons more strongly. Okay, so harder to remove them, right, in terms of ionization energy, because those electrons are more strongly attracted, right, in terms of electronegativity. That's the attraction that the atom has for those electrons. So the reason that it increases across the table and decreases down the table is essentially exactly the same as that for ionization energy. Now let's just take a quick look here. Here are some electronegativities versus atomic number, and we can see we increase the electronegativity as we go across the table. Here's a different chart here, a table of, this is a table of electronegativities actually. So you can see the most electronegative atom is fluorine and the least most electronegative is francium, right? It shows in this table francium and cesium both at 0.7, but actually francium is a little bit lower. This is just a 1 decimal place. If we looked at 2 decimal places, francium's would be a little bit lower than cesium. Now, electronegativity, we said it increases this way and decreases this way. All right, so it increases as you go up the table and as you go across the table. By across, I mean from left to right. Yeah. Now, we can note actually that the noble gases, oh no, someone forgot to write their electronegativity. Well, no, they weren't forgotten. It's just that, how do we say this? We can't say they don't have electronegativity, right? We can't say that they have none. That's why it's not listed as a 0.0, right? But the noble gases' electronegativity just doesn't even apply to them, right? So remember, electronegativity is the attraction for bonding electrons. Well, the noble gases don't react, do they? They don't form bonds with other atoms, so they don't have any attraction for bonding electrons. The concept doesn't even apply. We can't say their attraction for the bonding electrons is 0 because the concept doesn't even apply to them because they don't form bonds with other atoms. So it's not that it's 0, it's just that it means absolutely nothing with regards to the noble gases. Okay, so that is electronegativity. Now, the last thing we're going to look at very quickly is the melting and boiling point. Essentially, the melting and boiling points peak as we go through the D and the P block, and then it drops off. Okay, so it kind of looks something like this. Okay, so here these are the D block elements, and here we have the P block elements. And you can see as we start going across the D block or across the P block, that melting and boiling points is peaking there. The bonds are stronger with half-filled orbitals. So if the bonds are stronger, that's going to increase the melting and boiling point. Okay, so with these half-filled Ds and Ps, we have stronger bonds, so a higher melting and boiling point. So there we go. There are just a couple of trends that we can notice as we look across or down the periodic table.
don't forget to hit the like button. Yeah, and subscribe too. It's up here. And here's another video.